All right, recording started. Last time we stopped here at the transformer protection. So the transformer protection has two things. The first thing, which is called physical or mechanical protection, and the second one, which is called electrical protection. The physical protection is most likely associated with hardware and environments. Hardware and environments. However, the electrical protection related to voltage, currents, frequency, voltage, current, frequency, flux, etc. So anything related to electrical quantities, while anything related to hardware and environment, like the temperature, like the oil pressure, and the other thing, like the winding temperature, the transformer temperature, this is related to physical or mechanical protection, while again, anything related to voltage, current, flux, frequency, this is associated with electrical protection. So physical protection, like the protection used to in internal faults, which is called the Buchholz relay or Buchholz relay. The other one, which is the protection against winding overheating, which is the winding temperature. And the protection in oil overheating, the oil temperature, oil pressure, which is pressure oil, pressure relief, and the oil level in the conservator, which is again oil level. Then there is another like type of protection, which is for electrical protection, fuses. Fuses are basically elements that are detecting if there is any high currents, which is it will be melts or like wire will melts at high currents. So the thing, when there is high currents, this makes the high current makes high temperature. This high temperature will melt the wire, will melt the wire because it's made from material that will be melted until once it's reached a certain temperature. Therefore, we have fuses like, for example, 10 amps fuse, 20 amps fuse, or 100 amps fuse, etc. This is detecting overcurrents or detect high currents. So basically, it works under high currents. High currents, which makes, what does it mean? Overload or short circuits. If there is overload currents or if there is a short circuits going on, it will detect it, but then the fuse will work. The thing about the fuse, it must be replaced. It must be replaced after each trip. Once there is a power outage, then you need to replace the fuse, put another one to solve the problem. So therefore, the fuses, it's cheaper than the other type of protections, but the problem on the fuse, once it is being tripped or the power is out, you need to replace the fuse, which will cost some money. So therefore, we will put the fuse in areas where there is a less chance of getting faults, and where are like the areas that are not very important. So if there is a power outage, I mean, the utility company will send the technician there to replace the fuse. So this will take some time. As a result, the fuse, it is something that, it's not desired, but I would say like it will be not reliable in very important areas when there is a load is important, or not very reliable in areas where we have a frequent faults or a frequent power outage. The other type of the protection, which is called overcurrent protection, using the circuit breakers. Then there is earth fault protection, which means if there is a fault going on inside the system, like line to ground faults, then there will be some current going through the ground. Then the system will detect there is a current on the ground. The ground shouldn't have a current. The ground's current must be zero in normal operation. If there is abnormal operation, there will be some current going into the ground, which make it when there is detection, when there is a current in the ground detection, which make it there is abnormal operation, there is something wrong happening, like faults or some problems going on in the system. Therefore, the circuit breaker will trip in this situation. The other thing, the restricted earth fault protection, the same way. There is a differential protection. Differential protection, we will again talk about overviewing the protection later, but the differential protection, most likely this is used in the transformer a lot. Like here is the transformer. Then we are detecting the internal current going on here, how much the currents. Then detect how is the currents outer. Then in per units, make them in per units. In per unit, they must equal to each other. So the thing, does IA equals to IB? If yes, in per unit again. I mean, if it's not in per unit, of course, they are not equal to each other because stepping down, making the currents high. Stepping down the voltage will step high the currents. But here in per units, we will make and see, are those equal to each other? If yes, then it is normal condition. If no, it is abnormal, which means there is a leakage current or a path for the current like fault going on. If there's a fault going on, then IA will not equal to IB in per units. That's the thing, which is called in differential protection. Again, this differential protection, and overall, again, you will talk, or we will talk a little bit about it later in protection section. But the other thing also, there's a different, there is a course, separated course called protection systems. Then you will hear in deep details about the differential protection and learn how this thing works. There's the other thing, overflux protection, over voltage protection, under voltage protection, surge protection for like lightning strikes, and under frequency protection. All of them, those are type of protections to protect the transformer. The main reason for using this protection, the transformer is a very expensive equipment. So we don't want to have a severe damage to the transformer or anything that impact the transformer. So we can spend money on the fuses or spend money on the protection, while we don't want to spend to replace the transformer. We can replace the fuse, we can replace the circuit breaker, whatever we have, but we don't want to replace the transformer because it's in millions. Which electrical protection device to use? This is actually depending on the transformer size and depending on the location. For example, the distribution transformer, DT, in the distribution transformers, we are using the fuses alone. While if we are on the power transformer, it depends on the ratings. Distribution transformer or low voltage, we are using fuses. In medium voltage, we can use either fuses or circuit breakers or differential protection, which is circuit breaker over current protection, I would say, like over currents. Or differential protection. In high voltage and extra high voltage, we will use differential protection. No fuses, of course. Why there is no fuses in medium voltage or even in medium voltage in higher ratings, there is no fuses. And in higher ratings of high voltage and extra high voltage, we don't want to use fuses, because if there is a fault going on, there will be a power outage on all of the system, and we need to replace the fuse, which will be inconvenient to send the maintenance team and replace the fuse, which will take a lot of time and a lot of power, a lot of duration for power outage. And the other thing, there can be some frequent power outages and due to temporary faults, not due to permanent faults. Temporary faults can be, for example, there is a tree branch going toward the power lines, which will cause overcurrents. Then the main reason for, then the branch of the tree will fall down on the floor or on the ground. So once they fall down, the main reason for the fault will disappear. Therefore, this fault is temporary. It's not lasting forever. then why we need to disconnect the power for a long period of time, why we need to send the maintenance there to reconnect the power. So there is no need for that. So as a result, the National Control Center, NCC, will re-energize the power system, which there will be, I mean, once they re-energize it, they will realize there is no fault. The fault is no longer exist. Therefore, we return the power service, return the transformer and the power lines back in service without sending the maintenance team, or we will return the service in a few seconds instead of waiting hours or waiting maybe 30 minutes to 1 hour to send the maintenance team to fix the problem or to replace the fuse. So the higher voltage or the higher power, the higher risk, then let's use the more or spend more money on the protection by using the overcurrent and the differential protection. However, on the other hand, when you talk about the low voltage, where the faults are very rare or not very common. And the other thing, we don't want to spend a lot of money on distribution transformers because if there is power outage, the customers will call the utility company, then they will send the technicians there, they will replace the switch, they will replace the fuse, solve the problem, replace the fuse, then let the power back to service. So again, when we're talking about the capacity below than 2.5 megawatt volt ampere or 2,500 kilovolt ampere, let's use fuses. If it is between 2.5 mega to 5 mega, then we can use fuses in lower ratings, but sometimes we can use instantaneous overcurrent protection. If between 5 mega to 10 mega, we are using protection like differential protection or overcurrents. If it is above 10 megavolts, then we will use differential protection. Again, in this situation, number 1 is used only for low voltage, while number 4 is used for extra high voltage and high voltage, while number 2 and 3 are used in medium voltage. Okay? In practice, differential protection is the most commonly used, which is the best thing, is to use differential protection everywhere. But why we are not using it everywhere? Because it sometimes can be expensive, can be more complicated, then therefore in low voltage there is no need for differential protection. Now the other thing in the power systems, which is there is the surge arrestors. The surge arrestors, it can be in the power system, not only inside the transformer, it can be outside the transformer, which is at the beginning of the power lines. And the surge arrestor's purpose is to take the lightning strikes, and the lightning strikes will go through it. So when you look at the surge arrestors here, this is from the substation, you will see that there is a meter here, or there is a count meter here, a counter. This counter, it's also here, will detect how many faults. This counter, how many faults. Or not how many faults, or how many lightning strikes, I would say. This is the exact expression. How many lightning strikes? How many lightning strikes are there? If there is lightning strikes going on, then it will be count 1. Then after 1 day, another one, it will be counted 2. So it will be cumulative. It will not be resetted unless the engineer will go there and do the maintenance there. The other thing, arcing horns, this is they will be in the either insulators and can be in the bushings of the transformer from high voltage surge. So this is happening to discharge the power. They are using it to discharge the power during flashover or during the lightning strikes. So to protect the either the overhead transmission lines or the bushings of the transformer or the switchgear from damage due to overvoltage or lightning strikes. When there's a lightning strike going on, then we need to discharge the energy because sometimes the air will be ionized. So if the air ionized here, it will cause some damages to the bushings. However, once we put these arcing horns, the air will be ionized here. So the discharge will go in here, will go in on here, from the bushings or from the horns toward the body of the transformer. So it will create a path for the discharge better than, if it's not exists, the air will be ionized here. It will cause the discs or the bushings to be damaged. While once we create this path, it will not cause a damage for the point. So we are making the path easy for the currents to flow into the body of the transformer, but it will not be very big. It will be just like flashover, something we call a flashover. You will see this a lot, in power quality course, in case if there's a power quality course in your curriculum, this is one of the common things that's happening, especially when there is over voltage or there is a lighting strikes. Here is the cross-section area of the, here's, the side view, the side view of the transformer. When you look at it, this is the transformer, there are fans, and there is a radiators, and there's a motor drive. There is a fan, then we can say, and this is made from oil. So there is oil, and there's fan. So we can say oil, natural air forced, enough, but there is a radiator and motor drive. Radiator and motor drive, they are used for the oil. Therefore, I would say it's not oil natural. Oil forced, air forced. Oil forced because there is a radiator and motor drive for oil circulation. And air force because of the fan. Air force would be external cooling method using oil, using fan. Oil force, internal. So this is external cooling, and while oil force, this is internal cooling. And we already talked about the cooling before, in the last lecture. Then we can see also the bushings, the lightning arrestors for inside or for the transformer. Those are the bushings, high voltage bushings and low voltage bushings, as we see, the cable connector, the low voltage lightning arrestors as well, and the power cable. Here is the top view. Then in the top view, you can see, here is like the connection, the bushings, high voltage bushings. Those are the low voltage bushings. Then we can see the Buchholz relay here. And here's the conservator, the reserve, the conservator, the main tank. Then you can see the pressure relief tank. And the other thing here is another side view. You can look, you see the conservator. Here is the Buchholz relay. Those are the high voltage bushings, the low voltage bushings. The oil level indicator is already here. Then the breather or the silica gel are here. You see the silica gel are here. Then the winding temperature sensor will be here as well. Okay. Now let's go to talk about the transformer connection. We already mentioned the transformer connection before. Let me think about this. So the thing we already talked about, it can be Y to Y, Y to delta, and we mentioned about Y to delta, there will be a phase shifts around 30 degrees or multiple of 30 degrees. So when we talk about this one, we see that here when we look at it, there is Y to Y connection. The disadvantage of the Y to Y connection is the third harmonics contents. What's the source of the third harmonics? It can be from the load side, like when there is electronics devices, anything with inverter driven, like nowadays we see the air condition with inverter driven, we see the refrigerator with inverter driven to save power, and we can see the washer machine with inverter driven, everything with inverter driven, and the EV chargers with inverter driven. So anything with inverter driven, anything with power electronics, there will be a third harmonics contents. The drawback of this, the third harmonics will move from low voltage toward the high voltage, the medium voltage level, if there is a Y to Y connection. So the harmonics will move from here to here. third harmonics. That's something undesired. That's why Y to Y transformer is not very common in power system because we need, if there is a harmonics in the low voltage, let's keep it in the low voltage. We don't want the harmonics to be shifted from the low voltage toward the high voltage. That's the point. And the same thing from low voltage to medium voltage. We don't want the medium voltage harmonics to move the high voltage harmonics. Then the other thing, delta to delta transformer. Delta to delta transformer is good, but the problem is there is no neutral. The good, there is no third harmonics. No third harmonics. But they want to move, there is no neutral. Then there is Y to neutral, delta to neutral. I'm sorry, delta to Y and Y to delta. Those are very common, but the challenge is there is a displacement, which is we call it phase shifts, 30 degrees or 30 degrees times n. So it can be 30 degrees, 150 degrees, minus 30 degrees, etc. That's something that's a problem. But Y delta and delta to Y, those are very common. Now there is a connection group, or there is, I would say, a labeling for the transformer label, or I would say like transformer names, which we call it connection groups. So what's the connection group? There is a letter to letter. The first letter for the capital related to the primary. If it is delta, will be D. If it is star or Y, it will be Y. Then the second one will be small letter, which is D and Y, which is indicates of the secondary winding. Then there is a number, which is for the displacement in multiple of 30 degrees. And as an example, assume there is Y, Y, 0. This means the primary is Y, secondary is Y, and the displacement angle or shift, the shift is 0. How about DD0? The primary is delta, secondary is delta, then the phase shift is 0. How about YD1? The primary, let me fix it. Y should be capital, the first letter should be capital letter. YD1. So Y, the primary is Y, the secondary small, which is delta, then the phase shifts 1 times 30 will be 30 degrees. Then there is dy11. dy11, the primary is delta, the secondary is Y, and the phase displacement 330 degrees, because 11 times 30 will be 330, or in other words, we can say 330 is the same as negative 30 degrees as a phase shift. This is very common in our distribution transformers. Common in distribution transformers. dy11. Okay? Let's look at this chart. These, summarizing everything. So we have y0, primary is Y, secondary is Y, the displacement is 0. DD0, primary is delta, secondary is delta, displacement angle is 0. Then there is a zigzag, DZ0. What does zigzag mean? We already discussed the zigzag in the previous chapter. We mentioned that the substation, it has a transformer, which is called auxiliary transformer or grounding transformer or zigzag transformer. The main purpose is to provide the neutral for the substation or the distribution, and the other thing to provide power to the electrical, or to provide power to the substation, or the switch gear, because the switch gear, we need to have power for the lights, power for the air condition inside the substation, power for the switch gear, the equipments, the CT, VT, all of them, that we need to power them up. Then we can power them up using the zigzag transformer. So again, this is called DZ0. This is the zigzag transformer. Then the other one there is YD1. The primary is Y. The secondary is delta with displacement angle 30 degrees. And then dy1, the primary is delta, secondary is Y, then with 30 degrees displacement. Then the yz1, the primary is Y, secondary is zigzag, and the displacement angle is 30 degrees. Then the same thing here. Here we have two 2, this means displacement was 60 degrees. Then we have DD2, which is the primary is delta, secondary is delta, and displacement angle 60 degrees. Then DZ2 as well. Then we have here the number 4, which is 4 times 3, which is 120 degrees, which is applied in DD4 and DZ4. Then number 5, which is 150 degrees, which is YD5, which is Y to primary is Y, secondary is delta with 150 degrees, and dy5 as well. Primary is delta, secondary is Y and 150 degrees. Then YZ5 as well. Then we can say there is a 60, which is 180 degrees phase shift, as we see in YD6 and DD6. So it's very important for you to understand what's the primary, what's the secondary, and what's the displacement angle once you look at the symbol. Then YD7 and DD8, etc. There is YD10, 330 degrees, 300 degrees, I'm sorry. Oh, this is 300 degrees, then this 330 degrees. Okay, there is no number 12. Why? Because number 12 means 360 degrees, which is the same as 0 degrees. So we just stop at 11, number 11. Then YD11 and DY11, YZ11, you need to know what does it mean, each one mean. 11 means 330 degrees. The capital letter means the primary. The small letter means the secondary. And the Z means zigzag. Here is a nameplate. Here is this picture for the nameplates of the distribution transformer that we are using in Jordan. The distribution transformer, when you look at it, it's very small rating, 50 kilovolt ampere, and the voltage 33 kilovolts, because this distribution transformer converting 33 kilovolts to 0.4 kilovolts. This is very common in Jordan. And when you look at the frequency, this is 50 hertz. Look at the vector group, dy and 11. So D means delta, primary is delta, and the secondary is Y or star, is Y. Then the angle here, since it's 11, means 330 degrees, or we can say negative 30 degrees. Then the other thing, the impedance, which is 404.46 ohms. We will talk about impedance later, maybe in today's lecture. Then the loading coordination according to the IEC standards. This IEC standards is very common to make sure it is being designed or it's being built that can satisfy these standards. Then the rising temperature, 45 or 55 temperature that can handle um, up more than the normal. Then when you look at the serial number, this is the serial number as well. The manufacturer, this is very old in 1993, and it's been used to be outdoor. There are some transformers can be designed indoor, especially in GIS substations. Then the cooling method, it's ONAN. What does ONAN mean? Oil natural, air natural, which means there is no fans, there is no radiators. The other thing, order number, when you look at it, is called GEA. What does GEA mean? It's being designed it's being built in 1993, which is when there is Jordan electricity authorization, سلطة الكهرباء الأردنية. So this means it's been designed for سلطة الكهرباء الأردنية, for GEA, but that Jordan Electricity Authority. So that's why it's too old. This is very old. It was used for GEA before the invention of NIPCO and ITCO. Before invention of NIPCO, GIPCO, and ITCO. The other thing, the oil weights. Here is how's the oil weight in kilograms, and the active part weights in kilograms, the net weights, including everything. The other parts, when you look at the data sheet, there you will see the which is called the tap changer settings. The tap changer settings, as we know, the tap changer will be applied on the high voltage, while in the low voltage there is no tap changer. Then you can see the voltage here around 415. So if you divide 415 divided by square root of 3, it will be, I think, 232, something like that. 232 or 235, I'm not exactly sure which one, but like, I would say like 235. Then, when you look at the ratings for these positions, I'm not sure if you have a clear image, but you can see that this one is 33.8. This one is 33 kilovolts. This one 32 kilovolts, 31 kilovolts, 30.5 kilovolts. Okay, those are the tap changers. And by the way, this tap changer, since it is in low voltage scale or distribution transformer, this is off-load tap changer. Off-load tap changer. What does off-load mean? Which means the technicians will go there and adjust the tap changer settings. It will not be adjusted automatically or remotely. It will be adjusted by, sending the technician will do that. While in high voltage or in medium voltage and high voltage, we have on-load tap changer. That on-load tap changer will be adjusted automatically through something we call a automatic voltage regulation, which is called AVR. While here, it is off-load tap changer, which make it, we cannot change the, we will send the technician there to do the tap changer. But now, again, our target or the thing to get the voltage 33 kilovolts. Why we have 33.8? Why we have 31 and 30 and 32? What's the point of this? This is related to the load behavior. If you have a light load, when you have a light load, which will make, a very high reactive power, which will make over voltage. So the voltage will be very high value. Therefore, we need to downgrade the voltage to be low. Why we need to decrease the voltage? How to decrease the voltage? By decrease the tap changer settings. What's the point of decreasing the voltage? We need to decrease the voltage because we have a light load, we have a capacitive impact, then we need to decrease the voltage. And if we have a heavy load conditions, and heavy load, there will be a lot of reactive power consumption. That consumption of, of reactive power will reflect on decreasing the tap changer settings or will decreasing the voltage. Once we are decreasing the voltage, we need to increase it using the tap changer. That's why in the morning, early morning, I would say in high voltage and medium voltage, early morning, you will see the tap changer will be adjusted in very low value. And once we have a high power consumption during the day, there will be high power consumption. The tap changer will start switching from one stage to another stage to compensate with the load. But here in this transformer, we are talking about only offload, which means we will adjust it and keep it constant forever. Let's, for example, if we use the position number 2, we will keep it in the position number 2 forever. We will not do it, through the day. We will not send anybody to adjust it today in the morning and afternoon, readjust it. No, this is not feasible. So in offload, it will last forever. Let's use position 2, then we will use position 2 forever. When will we change the position? Assume, the customers, they will, when the customer is receiving a voltage, abnormal voltage, like the customer receiving a voltage 250 volts instead of 230, they are receiving 250 or 260 volts. This is very harmful for the electrical equipment at their homes. So they will file a complaint. They will go to the power company and file a complaint and say, we have a very high voltage. Then the power company or the utility will send the team to detect the voltage. Then they will see the voltage is 260. Then what they're going to do, they will go to the distribution transformer and switch the tap changer to a lower position. Once they switch it to a lower position, the voltage that received at the customer side will be reduced. Then they will keep it low forever. That's one way of changing the offload, changing only once. Or another example, assume there's a heavy load in that neighborhood, then there's a heavy load, then the customers, the end at the far end, the further at the far end of the customer, they are receiving a voltage around 180 volts. This is too low with respect to the 230 volts. Therefore, the customers or the file a complaint, the power company, they will come, the utility, and do their observation, doing their investigation. Then they realize, okay, we need to increase the tap changer settings. They will go to the distribution transformer and increasing the tap changer settings. Okay? And again, the tap changer will be only at the high voltage side, not at the low voltage, for more convenient, because the low voltage will be very sensitive in small variation, while in high voltage is less sensitive. Here is the other nameplate, but this is used in um, this is still used in distribution transformer as well. You will see that the frequency is 50 hertz. This one is used to convert 11 kilovolts to 230 volts. This is another distribution transformer. And this one is cooling method, which is on. And this one, there's a tap changer, but this is a single phase transformer. It's very rare in Jordan, but we have some. And you see that it's for Jordan Electricity Authority, GEA. سلطة الكهرباء الأردنية, and it was in 91 سنة 1991. Oh my god, it's too old. Okay, then we see that the tap changer settings in the high voltage side, 11 kilovolts, 11.5, 11.2, and 10.7, and 10.45. Okay, any question? Again, this way, this is a single phase, while this one is the three phase. This is the power transformer that's used in extra high voltage, or I would say like high voltage level. So the voltage level here, it's written as 145 to 36 kilovolts. Actually, it is for 132 kilovolts to 33 kilovolts. But why we have, it can handle up to 145 and can handle up to 36? Because of the tap changers. The tap changer can do the job. Okay, so look at it. You will see the rated power is 54 or 54,000 kilovolt ampere, or in other words, I would say 54 megavolt ampere. This is if it is on. And what does on mean? Oil natural, air natural. However, if we are using ONF, we can increase the ratings to be 80 megavolt ampere. 80 megavolt ampere. Now, why, when we switch from on to on-off, we are increasing the power? The answer is, when you increase the amount of power, what's happening, there will be some losses in the transformer. That losses, as eddy current losses and core losses, will be dissipated as heat. That heat, I mean, the transformer has a certain heat limit. Once we exceed that temperature, it will cause a permanent damage. However, when you are increasing or when you are turning on the fans will reduce the temperature. Once we are reducing the temperature will be reduced. Then we have more room. Then we can increase the amount of power to be 80 megavolt ampere, so it can handle higher currents. Okay? So on and on off. So therefore, in this type of the transformer, we have fans that are switched off. They will be switched on once it's necessarily. When we increase the power, when it's reaching 50-ish, like 50, 51, 52 megavolt ampere, then the fans start to be turning on. Therefore, we can have more room to use to power up the transformer for more values. The number of phases is three. It's three-phase transformer, the 50 hertz, and the connection group Y, D. Y and N means where there is a neutral. Y and D1. What does mean? The primary is Y, the secondary is delta, and the angle 30 degrees. Okay? The other thing, the temperatures rise 55 degrees for the windings, for the oil 50 degrees. Then the classification, as I said, like there is a tap changer, that's why we have 45 to 36. kilovolts. Then the cooling type, it can be on and or on off, and was manufactured in 2007. Serial number here, we don't have it here, but it's according to the IEC standards, which is 76. Then the total mass, as we see here, the transportation mass and the oil mass, etc. The ranking. Then when this here is like the vector group, and this is the connection group according to, we see here it's Y connected, and here it is delta connected on the other side, in the secondary side. Then when you look at the windings or the tap changer, there is no tap changer here, in the no taps on low voltage side. While in high voltage side, there's tap changers. You can see like there are, I would say, 14 positions. This is, I mean, a lot. There are 14 positions. In these tap changer positions, those are use on-load tap changer. On-load tap changer that will be switched automatically. How can be switched automatically? Through something we call it AVR, which is automatic voltage regulator. So the AVR will be switch between the taps automatically without a human control. It will be switched automatically to make sure to maintain voltage level, to make sure that the voltage level is fine. If there is a lower voltages, which is basically if there is a heavy load, will cause the voltage to be reduced. Then the transformer, it will detect the voltage is getting lower, then increase the tap changer. Then if there is a light load, there's a light load going on, then the transformer understand there is a light load going on. Once there is a light load, the transformer, once there is a light load, the transformer will send the command the tap changer to decrease the taps. Okay? Any question? So far, so good? All right. Now, let's talk about parallel link transformer. What's the point of the parallel link transformers? Let me see. All right, okay. Do you remember when we talk about the switching? Let's see. Okay. The switching, here is the single line diagram. Here's, for this example, look at this one. In this example, single line diagram, there was two transformers. There's one transformer here and one big transformer here. What's the point of these two transformers is to have n minus 1. In Jordan, we used to have n minus 1. What does n minus 1 mean? If there is STR1 was out of service doing maintenance, STR2 should take care of the loads. And the vice versa. If there is a fault going on, the vice versa. That's happening. Then, if there is a problem on ATP circuit number 1, the ATP2 should take care of it. If there is a problem in the first bus bar, this part of the bus bar, the second half of the bus bar should take care of it. This is called n-1. This is very common in high voltage and extra high voltage in Jordan. Therefore, as a result, this yields to be STR1 and STR2, both of them, they are in parallel. This is a must. They must be in parallel. Then when we look at it, those are in parallel, then we cannot put any transformer in parallel without taking into consideration they must share the same voltage, 132 to 33 kilovolts, 132 to 33 kilovolts. They must share the same ratings, 40 megavolt ampere, 40 megavolt ampere. They must share the same vector group, Y and D1. Y and D1 is a must. So there are some conditions for the paralleling. Let's talk about them here. So we need to have, they must be with the same primary and secondary voltages. They must be with the same phase rotation, phase sequence. If they are both positive sequence, negative sequence, they must vector group displacement angle 30 degrees, they must. Turns ratio, it's recommended, it's very, I mean, we must have it, but, and the percentage impedance, it's very recommended to have it. So the first and second condition, same voltage and same ratio, if they are not satisfied, the parallel operation will not happen. What's happening if they are not the same voltage and if they are not the same vector group? The parallel transformer will be they will be understandable as line-to-line faults. So if they are parallel, it will be, we will understand it as line-to-line faults, not as parallel transformer, which will cause a problem. So it will not be feasible. The other thing, if same voltage, same turns ratio happening, same rotation happening, but not same turns ratio, it will cause overheats on the transformer, and that will cause impact the lifespan. So the transformer will not last time. Therefore, we don't want this to happen. So the first three condition is a must. How about the fourth condition, same percentage impedance? If it is not met, they will not be equally shared for the power. What does percentage impedance mean? We will talk about it. Let's talk about the impacts, the negative impact for not equal the same percentage impedance. Assume you have a transformer with a ratings 100 megavolt ampere, and you are paralleling with a transformer with a ratings 40 megavolt ampere. If they are not sharing the same impedance, this one can be loaded with, for example, 35 megavolt ampere. This one will be loaded with megavolt ampere. The biggest amount of power, I don't have an access to go to the 100 megavolt ampere. It will go toward the worst situation. Assume this one is loaded with 50 megavolt ampere, while this one is loaded with 30 megavolt ampere. This make overload on this one. Here is overload. While here it's still underload. And that can happen if and only if they are not sharing the percentage impedance. However, if both of them sharing the same percentage impedance, they will be loaded equally. If you have here 20, then this one must be 20, and so on. If this is 30, this one will be 30. They will be loaded equally if and only if sharing the same percentage impedance. Okay? Okay, so the percentage impedance, which is basically for the transformer, it will tell us about the currents, where is the current flow in each windings. So how to test or to measure the equivalent impedance or the surge impedance by doing this job, which is basically, here's the transformer. So what you will do is to put a voltmeter here. So measure how much the voltage. So the voltage here, delta V, is basically, for example, we realize volts drop. Then look at the primary voltage here. The primary voltage is, for example, in this example, 2,400. To calculate the percentage impedance, it will be the delta voltage or the voltage drop divided by the V primary. So it will be 72 divided by 2,400 times 100%. So it will be 3%. Okay? This is how we calculate in real life the percentage impedance by measuring the voltage drop across the transformer terminals. So there's a 72 volts drop. What's the reason of the 72 drops? The physical reason, due to the losses of the transformer. There is a winding losses and core losses. 2% of these 72 voltage drops are due to the core, while the vast majority of the will be in the winding impedance or the winding of the transformer. This is the main reason for that. Okay, if the transformer is not operated at full load, then the voltage drop will be less. So the voltage drop might not be sufficient to determine it. So what we need to do, we can say measure how much currents there. Then you can say Z equals the voltage drop divided by the currents. Then we can use it as impedance in ohms. Transformer polarity. The transformer polarity is very important, especially in paralleling transformer. If, for example, one of them positive polarity, negative polarity, then there will be, when you parallel them, they will not be, we will understand it, or the circuits will understand it as faults, as line-to-line faults, not as a transformer in parallel operation. So we need to make sure the three-phase polarity is fine. Now we can say we can create the three-phase transformer. Three-phase transformer can be created from connecting three single-phase transformers. Or we can use the original three-phase transformer. So we have these two options. You can connect three single-phase transformers to be a three-phase transformer, or you can connect three-phase transformer. Okay, so the way that we can make the connection, we need to make sure with the angular displacement, as I said, like YD11 or YDY11, etc. Phase rotation as well, sequence the direction of the rotation. Okay, the polarity is very important when you hook up the transformers for the protection and metering as well. The transformer polarity, depending on the direction, it can be either clockwise or counterclockwise. The transformers are sometimes marked at their terminals with polarity marks, and there should be a polarity for the transformer, the polarity marks. Usually the polarity marks shown in white painted dots for plus, or plus minus marks on the transformer. You can see in the name plates there's a plus minus, or you will see a white painted dots. This makes it the transformer. Most likely, the transformer polarity is simply following the American National Standards Institute, which is called ANSI, and donated for H1, H2, X1, X2. So the terminal H1 located in the right-hand side when facing the high voltage side of the transformer, while X1 and X2 related to the low voltage side. Okay. Now the other thing, which is the here is how it looks like. Then we can see H1 and H2 are related to the high voltage side, while X1 and are related to the low voltage side as well. Low voltage side. Then when you look at this one, there can be something we call additive and subtractive for each one. Here, this is the negative, this is the positive, negative, positive. Because the top of the arrow will be at the positive side. While this one, negative, positive, here is negative, here is positive. So, which is called subtractive. Part B, called additive. How can you? You can also look at the current direction, the current entering, the current here is entering, the current is leaving. Then when you look at it here, you can do KVL. When you do KVL, you will realize that's called, for example, this is V secondary, this is V primary. When you do KVL, plus V secondary minus V primary. So it is subtractive. While here, this is V secondary, this is V primary. Do KVL here, which is minus V secondary minus V primary, or you can say plus V secondary plus V primary. Then it is additive. Okay? That's how we understand this is additive or subtractive. So it's very important to know how to do that. So they said usually the high voltage side H1 will be, or I would say like H1 in the high voltage level. So if X1 on the left, which is subtractive polarity, if X1 on the right, it is additive polarity. But this is not common. It's common if and only if we are fixing H1 and H2. If they are changed the way that I like, which is what I did before. When you do KVL here. When you do the KVL, if they are equal, if they are like this, then it will be additive. Adding. If they are one positive, one negative, then they will be subtractive. This is the best scenario. Then the other thing is the current direction. The current, when you look at the arrow here for the voltage, then the current will leave the arrow. Here is the current, then it will leave like this. This one leave like this. Here the current, which make the current going this way. Here the current, the arrow will make the current going this way. So as a result, it's also the polarity really matters related to the current direction as well. Then we can say that the additive and the subtractive, this is how we can do it. Additive polarity is common in small distribution transformers, while in large transformers, such that the generator step-up unit GSU transformers, power planets, are usually subtractive polarity. So I would say in high voltage, extra high voltage power transformers, or even like low, medium voltage power transformers, we are using additive, subtractive, I'm sorry. However, in low voltage, not all of them, some, we will use additive. But also we are using subtractive. The very common is to use subtractive, not the additive. Additive is very rare. Then at any instant, when the current direction is into the polarity marked in the terminal of the primary winding, the current direction is out of the terminal, as I said earlier. So if it's the same in the connection circuits, there will be across two windings. Here is for the transformer, for the additive and subtractive. How can we know this one is additive or subtractive? I mean, on the connection, we couldn't see, but we can do it, tested it in the lab. Basically, here in this primary side, we applied 240 volts. Then we put the voltmeter readings between H2 and H1. The reading is 216. The 216 here is lower than 240. Therefore, it will be subtractive. Then the other one, here 240, and this is 264. Then the 240 and 64, we can say 264 larger than 240 volts, therefore it is additive. Okay? Let me stop here. We will continue, inshallah, next lecture. Let me stop recording. Any question?